Hey everyone, in this video I'm going to talk about what are called uncoupling agents. These are compounds that interact with the electron transport chain and the inner mitochondrial membrane in a certain way. And what they do, they allow the electron transport chain to still operate, so protons are still going to be pumped as NADH and FADH2 donate their electrons. However, it's going to eliminate the proton gradient. And as a result, it's going to bypass ATP synthesis. All right, so let's just draw a schematic view then of our inner mitochondrial and outer mitochondrial membranes. So this is the outer, this is the inner, this is the cytoplasm, this is the matrix. Okay, and in between, this is the inner membrane space. So recall then, we have complex 1, 2, 3, 4. I'll just line them up right here. 2, 3, 4. Okay, and let's just say, for example, NADH is dumping its electrons now off to complex. Okay, those electrons are going to flow through, ultimately go through, take oxygen to water. And along the way, we have protons getting pumped. H plus is there. It's a proton pumped at complex 3, and then one pumped at complex 4. Okay, so that would be the normal state of affairs when the electron transport chain is operating. And then recall that we have ATP synthase over here, which is this sort of large complex where the protons are now going to flow back through. And we're going to take ADP and convert it to ATP. So this is ATP synthase. So that would be the normal state of affairs. Again, the protons flow back through and we can make lots of ATP. However, there are molecules and even proteins that can disrupt this chemical gradient. So you may recall I mentioned that the inner mitochondrial membrane is a very well-sealed membrane. There are no holes or pores in it, except for the presence of these ATP synthase molecules, which contain these proton channels. But what if we were to add something that could, instead of allowing the protons to go through this channel, what if it just could come across the inner membrane all on its own? That's what a chemical uncoupling agent does. It is a compound that basically grabs a hold of protons and can allow them to diffuse across the membrane, basically bypassing the ATP synthase. So I'm just going to erase this just so that I can now draw in what might happen when you add an uncoupling agent. So these are still my two membranes. And the uncoupling agent that I'm going to specifically talk about is a protein called thermogenin. Okay, this is an actual protein that can diffuse through the inner mitochondrial or outer mitochondrial and inner mitochondrial membrane. And as it does this, thermogenin, it's a small protein, it's going to pick up these protons. So envision now, it's basically acting as a proton carrier. And what will happen now, once we get into the matrix, this thermogenin is now going to dump off its proton into the matrix. And then it's going to recycle. So this can now go back out, okay, and then go through the same process again, picking up a proton, dumping it off. So here, we essentially now have a bypass of this channel over here with ATP synthase. Now, what is the consequence of this? Well, one of the things that's produced as electrons flow through the electron transport chain, heat is generated. So this compound, thermogenin, is produced in animals that require additional heat, such as us. We are warm-blooded animals. And so thermogenin and similar types of proteins are responsible for the fact that we are able to keep our body temperature up above ambient temperature. So what are the consequences of this? So thermogenin, an uncoupling agent, does the following. So uncouplers allow ETC to work. Okay, so the electron transport chain is not disrupted in any way. Protons are pumped. However, because these protons now have an alternate path, and this is a much easier path to go through. Remember, ATP synthase is a motor protein. Okay, so in order to get this to turn 60 degrees and go around, there has to be a certain pressure, if you will, or a proton motive force to push these through and make that ratchet turn. If this is present, this bypass, no H plus through ATP synthase. Therefore, no ATP is made. Okay, however, recall I mentioned that heat is generated. Let's just put heat is generated. Okay, so this molecule thermogenin, it turns out occurs in different times of development in humans and other animals, and is a major component of certain types of adipose tissue. So on the next slide, I'll show you and talk to you about the types of thermogenin and applications in mammalian systems. Okay, so to finish up our discussion of uncoupling agents, I'm going to focus on this protein molecule called thermogenin, and just go through a couple examples of how this might work. So in humans and many other mammalian systems, let's look at a newborn infant. Okay, so you may, if you've ever been around a newborn infant, you've probably noticed that they tend to have this stuff called baby fat, right? They tend to have kind of very swollen features. They're kind of big and puffy. Well, why is that? Well, it turns out in utero, before the birth, about a couple months before gestation is completed, there's a developmental thing that will happen in adipose tissue where thermogenin is going to be built up in the adipose tissue, in fat tissue. And essentially what that's getting ready for is once the birth happens, the baby comes out of the nice warm womb and is now in a very hostile environment that's often very cold. And so babies need to be able to regulate their body temperature. Okay, so this thermogenin now is going to act as a chemical uncoupling agent, okay, and it's going to allow the electron transport chain to continue. It's going to generate some heat. However, it's not going to produce a lot of ATP. If you've also been around newborn infants, they basically sleep, cry, eat, and do that other thing, okay? That doesn't require a heck of a lot of ATP. It's not like they're getting up and running a marathon or anything and need ATP, but they do need heat. So a newborn infant has a significant amount of thermogenin, which actually has a brown color. That's why this is often, baby fat is often called brown fat. And then throughout development over the next several months, as the baby starts to grow, becomes more active, starts to need to crawl and maybe walk, this baby fat or brown fat now starts to get converted to regular adipose tissue. Typically, an adolescent child now starts to thin out, and that baby fat goes away because now they're starting to need that ATP so they can start moving around. So that's one example, a newborn infant. A second example would be hibernating animals. Okay, so think, for example, a bear, either a grizzly bear or a black bear. You're probably aware that in the fall, a bear will typically start to gorge themselves on any type of food that's around, whether it be berries or fish or whatever they can get. They're basically storing up fat stores for the long winter. Well, as the sun cycle starts to get shorter in the day, some signals start to happen in the neurophysiology of the bear that start to trigger the formation of more thermogenin as they're depositing all that fat in their adipose tissue. And the reason for that is that when they go into their den to hibernate, it's still quite cold outside, but the bear now needs to regulate their body temperature so they don't freeze, but they don't need ATP very much because all they have to do is breathe. They're not really getting up and walking around or anything like that. So this allows a bear to sleep, okay, but no activity. Okay, and that's because there's not very much ATP that's being produced. So these two examples then just show how this molecule, this chemical uncoupling agent, can again allow the electron transport chain to flow, that will result in a production of heat. But that proton gradient that's formed is now not going to go through ATP synthase. It's going to go through thermogenin and bypass the ATP synthase. All right, so that wraps up our discussion then of uncoupling agents. I hope that helps.